Hi, in this video, we're going to take a look at using clustering for blocking in experimental design. Okay, so in clustering, what I'm trying to do, I'm looking at my independent variables, my predictor variables, and I want to group the rows of my data, the observations, into similar subgroups. All right, now in blocking, I have independent variables that I'm not interested in. They may or may not have an impact on the target variable, the response variable, the dependent variable. And so what I want to do is in my experiment, I want to make sure that all of these variables that I know are present in the situation, but I can't control and I'm not interested in are handled so that they don't impact the final results of that response variable. So imagine that I'm going to go into a school, I'm going to do a study on different types of, let's say, reading curriculum. All right, well, let's pretend I have full control over what happens in that school. Well, maybe gender is an aspect. Maybe race could have an impact on the results of the study. Maybe the free reduced lunch rate aspect could also have an impact. Maybe the race. Okay, so what I want to do, I want to make sure that I have an equal number or equal proportion of females in curriculum one and curriculum two. I want an equal proportion of males in curriculum one, curriculum two. I want to have an equal proportion of each individual race in curriculum one and curriculum two. I want to have equal proportions for each ethnicity, so usually Hispanic, non-Hispanic in the United States, for curriculum one and curriculum two. And I want to make sure, like free reduced lunch rates, each level, and that varies state by state, how that's coded is, equal, I have an equal proportion in curriculum one and curriculum two. Now, achieving this can be very difficult if I have a lot of variables I want to consider. And everything I've talked about so far are categorical or possibly ordinal. And so it might be, so it's at least like an easier one to set up. What if I have like numbers going on? Maybe I have variables that could be involved, let's say like blood pressure, height, weight, BMI. We have, other, glucose, other things that may impact what's going on. And I have a mixture level of data so that it's kind of hard. Well, I could always bend those, right? Well, if I have enough variables, now it's going to get difficult. And I think most of the time, most experiments, they're going to identify the variables that they're not interested in that have the biggest known effect, and they're going to isolate on just those because, well, that's what makes sense. But you know what? We can do better because we have clustering. We can use unsupervised machine learning to go and figure out what our subgroups are for us. We figure out our subgroups. Now, for each individual subgroup, I'm going to walk up to the first cluster and I'm going to randomly assign, the different levels of treatment and control. I'm going to, and I'm, I'll do stratification also, and I'll go across every single cluster and do the assignment. And by clustering, I've got each group is going to be, pretty similar. Each individual in each cluster is going to be similar to each other. That way, when I take a cluster and I start randomly assigning, I know that within the clusters, I'm splitting up similar as possible individuals as I can. Now, now, the only time I would really want to do this is if I have a lot of independent variables to account for that I manually I can't do it. If I only had like two, let's say I had gender and race, I could manually go in and just make sure that the groups are one at a time, assigned. But when I have a whole bunch of them and it's not possible to get even groups, clustering can come in and help us out. All right, so in experimental design, blocking is used to reduce the variability by grouping similar experimental units together before the treatment assignment. And so I'm going to take the similar subjects and put them all into a block, and I'm going to randomly assign treatments for each of them. Well, when there's a lot of blocking variables, it can be difficult for me to identify homogeneous groups. All right, let's say I've got like 1,000 columns of variables that could be, impacting what's going on. I can't do this. I can't handle this. I've got all their blood work, all their, their height, their weight, all of these metrics on them. I can't do this as a human being. You know what? I don't need to do it as a human being. I'm going to let machine learning do the job for me. I'm going to do some unsupervised learning, and it's going to save the day. All right, so I'm going to use clustering to come up with the blocks for me. All right, so let's go ahead and prepare the workspace. Once again, I'm using R. I'm going to just make sure that I don't have any artifacts floating around in my workspace or moving everything. Then I'm going to set up so that I don't get blasted in the face by numbers. And I'm going to avoid scientific notation. And I like to use piping. Piping is nice and fast and clean for coding. It is a little bit slower than base R, honestly. The piping adds an additional layer, but I find that piping makes the code easier to read. All right, so let's go ahead and load our data and then cluster it. So what we're going to do, I'm going to apply hierarchical clustering to the hair eye color data set. Now, any data set could have potentially worked, but I tried to come up with something that it would resonate with like an experimental design textbook, and hair and eye color, it has sex, hair, and eye color. Got 3 columns in there, and so these are very easy to identify with with subjects for a study, and so this is very natural to consider for blocks. And so now all of my columns are categorical; they're normal or nominal data, and so I'm going to use the Gower metric. All right, so the Gower metric is going to give me a distance matrix for my rows of data. And then I'm going to do hierarchical clustering off of that distance matrix. If I had all numeric data, I could go through and use k-means. I could have used partition around the medoid, PAM. I could have used Clara. I could have used a whole bunch. I could have done Fanny. I could have done a whole bunch of other cluster algorithms that invoke numeric data. But most of the time, in this situation that I'm talking about where we can't do it manually, we're going to have a mixture of data. And so the DAISY function that implements the Gower metric in R, in the cluster package, handles multiple types of data. So I chose to go this way. That way, this is flexible and handle a wide range of things. All right, so the DAISY function in the cluster package does the Gower metric, and it handles mixed data types for us: categorical, ordinal, numeric. All right, so what I'm trying to do, I'm going to use the clusters to form the blocks in my experimental design instead of manually doing this and identifying things. So here, honestly, I only have 3 distinct, I only have 3 independent variables going on in the data set as they come in, 3 nuisance variables that I'm not interested in my study. And I could easily have done this manually, no problem at all, easy peasy lemon squeezy. But I want to demonstrate how to do this if code-wise, if I had 1,000 columns. All right, so let's go ahead and load our data. This is from the datasets package. This automatically loads into your workspace in R. I'm using a hair eye color dataset, and it is loaded as a table. So this is a 3-dimensional table. We have sex, we have eye, and we have hair. All right. All right, so in this format, this isn't suitable for our purpose. All the information is there, but you notice that it has counts instead of actual like raw values. So what I'm going to do, first and foremost, I'm going to convert this table to a data frame. Boom, on this step. Next, I'm going to convert the counts into rows of observations. Okay, so what's going on in this uncount step right here it's going to take these three male brown eyes with brown hair, and it's going to create three rows where they have sex is male, eye is brown, and hair is blonde. And over here, let's say this, I'm going to go 29. What's going to end up happening is that in the uncount step, it's going to create 29 rows of sex is female, eye is hazel, and hair is brown. Okay, and so as my total number of rows of the uncount data frame is going to be the sum of all the numbers on the table. Now, after I do that, so I'm using the frequency, so this step here is going to have 4 columns. There's going to be sex, eye, and hair. Then there's going to be frequency, which is going to be the numbers inside the table. And that's where the frequency right here comes from, FREQ. Now, remember, I'm doing an experiment. So I want to use random assignment. I'm going to go ahead and shuffle the rows. Using sample frac, the default fraction is 1, which what this function will do by default will take my rows and just shuffle them so that I lose any order that was already in there, which is something you want to do in actual experiments. And so now I can see 592 is the number of subjects I have in the data set, and there are 3 columns, and that's going to be sex, eye, and hair. Frequency was lost in the uncount step. So this command creates a frequency column. This converts frequency into individual rows and drops the frequency column, shuffle it, and then boom, I've got the data of my subjects as they come to me. And these are features that I don't have control over. This isn't something I can apply as a treatment. There is no influence I have over this. This is what it is with these subjects. All right, so let's go ahead and just take a look at the head and the tail of the data. So you can see that I don't see a pattern in the hair, the eye, or the sex because I shuffled it like that. Okay, so this represents my subjects as they come to me for my experiment. All right, so now let's apply Gowers' distance. All right, so here I'm going to use the DAISY function in the cluster package. There's my data frame, and I'm using Gower. Now I'm going to apply the hierarchical clustering to the DAISY distance matrix. And let's go ahead and plot this. All right, so this is hard to read because I have 592 individual observations. And so each observation, each row in my data set, when I do hierarchical clustering, gets its own leaf at the bottom of the dendrogram. 592 of them, there's so many of them, I can't read it. And you can see that I can't read the number of the row either. So I can see the overall shape. This is helpful, helps me understand what's going on. You can see that I have very discrete shape for my dendrogram. Okay? Well, you know what? Let's make this a little bit easier to interpret, easier to read. What I'm going to do is I'm going to take that data frame that I've got. I'm only going to look at the individual unique rows. I'll look at the unique rows to see what the distances end up being. So I'm going to repeat what I just did, but I'm going to get rid of my duplicate rows. All right, so here I'm reducing it down to distinct rows, and I'm creating row names on this. That's what this does. Then I apply Gowers' distance to hierarchical clustering, and then I plot it. So now let's take a look at what we get. Okay, so now this is what's actually going on in that dendrogram above, but it was hard for me to see because I had so many observations. All right, so what you want to do, you want to start with the similar groups first and work your way up with these because that's, I can read it at the bottom. All right, so I have blonde green female, blonde hazel female, blonde brown female. All right, so we can see that blonde females are in here. We see that we have black green female, black hazel female. So females with black hair are in this part of the dendrogram. We have brown green female, brown hazel female. So we have brown hair females. Now we have red head female. Now so all of these are females. All right. Now if I look and let's go now to this part. All right, I have black hazel male, black green male, and I can go through and just see down the line that all of these are going to be males. And yeah, just going through looking at this. Now we have males over here. We have females over here in this part, and they all have blue eyes. Here we all have blue eyes. So this entire part of the tree is blue eyes. Kind of interesting how this worked out. And then, so here, we notice we have male and female here, but we have brown hair, brown eyes, and we have black hair, brown eyes, male and female. So interesting how this set up. This wasn't what I expected, but this will still definitely work. All right, so now I want to so this is my clustering, my dendrogram, and depending on where I slice on the dendrogram determines what do I get for my actual clusters. All right, so here we see that we have very discrete levels because I use Gower systems because it's working on nominal data. All right, so here I could slice here, I'd have 4 groups, and each group is going to be relatively large. I could slice down here at like 0.2, and I would see that I would have very similar groups across the board, and I have something in the middle on this. Honestly, I would lean towards slicing lower for this purpose, because if I slice lower, then each subgroup is going to be more similar to each other. The problem with that is that I'm going to end up having subgroups that are very, very small. So imagine that I have, just a subgroup of 1 or a subgroup of 3. Okay, it's going to end up in my assignment. I could potentially, if I have very, very small groups, I would end up having, some imbalance aspects that, we'll double check to see if that happens on this. So my opinion is that I would want to do this no lower than what would give me 2 groups or 2 individuals in every group. So I want a minimum of 2 in every single group when I do my slice. That is as low as I would recommend. All right, so the choice of cut height, that's what I was talking about here of going horizontal and cutting the tree. The number of clusters or blocks depends on the chosen cut height, which also corresponds to the number of groups. Has a range of possible heights. Here I chose to go with height because that has a connection to interpretation on complete linkage. All right, so most scientists that I've talked to that know about hierarchical clustering have used complete linkage. So for the purpose of a science experiment, you're going to probably want to use complete linkage. Ward's D is also a good choice. That's what I use usually for like a non-scientific project. If I'm using this for like a machine learning project, it's also, Ward's D is also the default in scikit-learn, and I believe it's the default in SciPy also for hierarchical clustering. So it's a good choice. Ward's D works to minimize the standard deviation within groups. A lower cut height results in finer partition, while a higher cut height produces broader groupings. Now, the cluster homogeneity, the Gower metric ensures that categorical features are handled well, meaning clusters should ideally contain similar experimental units. This can be problematic when I have subgroups of a very, very small size, especially if it's odd numbers. But hopefully just with random assignment, it would like even out in the wash. If I go a little bit higher up on the tree, I can even that out. But I don't want to go too high because then I start having dissimilar people within the same cluster. All right, so let's go ahead and cut high on the tree. And let's go 0.8 for the height. So what this means is that I'm going to come up here and I'm going to slice across and I'm going to get 4 distinct groups. If I slice at 0.5, which I'll show in a moment, I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 distinct groups off of this. And if I cut even lower at 0.2, you can see that I'm going to have even more subgroups. Okay, so I'm going to take my hierarchical clustering. I'm going to cut at the chosen height. I'm going to create a table. And so here I can just see like how many I have in each cluster, in each subgroup. And you can see I have most in 1, then in 2, 3, and 4. Honestly, the size of the groups is not as important as how homogeneous are each group or how dissimilar they are. My goal is to have each subgroup be as similar as possible, but operationally feasible to be able to assign my treatment and control. All right, so let's go ahead and assign the clusters. And so we can see what's going on. Now, this unique statement, I put this here so that we can check that we have a variety going on. Now, I shuffled everything, so it's harder to spot, but I've got black, blue, and male. Let's see if we can find black, blue, and male. Scrolling down. Black, blue, and female, but no, that's not it. Nope, I can't spot it. It definitely is going to be in here, though. Let's see. All right. Well, we'll keep rolling on. I'll show you. The proof will be in the pudding in a moment. All right. So now let's go ahead and group by. And now what I'm going to do is I'm going to group my data by the clusters. So what I'm doing, I'm going to go into each individual clusters, and I'm going to randomly assign control and treatment. Okay. So how I do this is important. So first and foremost, I'm just doing the sample function. That's going to be fine, no problem at all. I want to make sure that I have a 50-50 split. Okay, 50-50 split is actually pretty easy as long as I have an even number of observations inside my cluster. I may or may not, and I want to write this programmatically so I don't have to think about it. Okay, so what is going to happen? Let's say for a moment I have an even number of groups. Okay, I'm going to go and I'm just going to go control and treatment, and I am going to make half of them are control, half of them are treatments, and just going to go along like that. All right, so as long as I have an even number of groups within the cluster, I'm going to have 50-50 control, 50-50 treatment. And then I'm just going to take that vector, randomly shuffle, control treatment, and assign it. Boom, I've got it. Now the problem comes up with my code if I have an odd number. All right, so pretend that this is not here. If that wasn't there, what would happen is in this code, what would end up happening is I would have every single time that I have an odd, I would have one more control than treatment. Okay. Well, if I have one more control than treatment, I'm overloading the control side systematically every single time. All right, so that by putting on the sample int of 2, so randomly it's either going to be 1, then 2, or 2, then 1, randomly. And so if it's 1, 2, this is going to be control treatment. If it's 2, 1, it's going to be treatment control. All right, so if there's an odd number on there, that means it's going to be a 50-50 chance of where do I get the extra. All right, and so this is the best I can really do. All right, and so now I'm going to go ahead and show you what we end up getting. All right, so for this, we can just go through, let's see. I've got cluster one, control, cluster one, treatment, cluster one, treatment, cluster one, treatment. And you can see that it's random. I've got 53 more rows. It's, shuffled. But like here, this is treatment and control. You can see that I've got, both of them present back to back. All right, so now I want to double check to make sure that I have things relatively even. Okay, so it's not going to end up being perfectly even. If it was possible to become perfectly even, honestly, I wouldn't be going through this exercise. But let's say that there's just so many things involved, it's going to be difficult to get evenness off of this. All right, so here, ideally, I would have exactly 50-50, but this is pretty close, not perfect. Ideally, I would have 50-50, close, but not perfect, and so on. 50-50 would be ideal, but things are relatively pretty close. And I can keep on. Now when I get to the clusters, you can see like I'm nailing it on the 50-50 aspect, across the board. All right, so now let's repeat this now, but I'm going to go with a moderate number of clusters. So here I went with very, very few. I cut up very high on the dendrogram. Now I want to go a little bit lower. I want to go like a moderate level. I'm going to cut at a height of 0.5. And so here I can see the number of observations in each cluster. And I'm going through and let's see, I've got cluster one, treatments, or I have control and treatments. Then I have treatments, and that, so it's at least as even as it can be on the first few rows being printed. All right, and just going down, taking a look, what's going on. Oh, actually, this is a carryover from the previous. Okay. Yeah, this treatment is actually from the last one. When we get down to here, that chunk of code should be removed. I'll do that for class. All right, so now I've got this all set up, and you can see that it's different groups now. There are more of them. I've got 5, and you can see that things are pretty even considering I can only see the first 10 rows. And now let's take a look at the even aspect. All right, so not perfect, but close. All right, it's even as it can be, and as even as it can be. All right, perfectly even as it can be. All right, not quite perfect, and not quite perfect. Okay, a little bit farther than I want, but it's not too bad. This is acceptable. And so, we can go down and we can see that, for the clusters, everything is as even as it possibly can be. All right, so now let's repeat this and let's go as low as I can. So I'm going to have as many groups as possible. And so that's going to result in each group is going to be as similar to each other as possible with this, but this is going to result in very small groups. So like group size of 1 might be a problem that potentially I'm more likely to have like, clumping off of this, just off of just random assignments. Well, like with the bigger groups within the clusters, I'm guaranteed to have evenness by how I wrote my code. All right, so you can see I've got 32 groups. Well, that's a huge increase to what I had before. I had, what, 4, then 12? And now I'm at 32. Wow, huge jump on that one. All right, so now let's just take a look at it, at what we get after I do my assignments. All right. Now let's go, and the 1, 2, 3, 4, 5, 6, 7, 8, 9 aspect, that is an artifact of how the hierarchical cluster labels. It takes the first few rows and assign those to group 1 just by how it's built up. Okay, so now let's take a look at the evenness this time. All right, that's really close to perfect. It's one off from perfect, as perfect as it can be, as perfect as it can be. All right, one off. as close as it can be, as close as it can be, one off, as perfect as it can be. All right, this see what if it had one more over, it's one off from being perfect. And you can see that with the clusters, once again, it did a really good job of making sure that my treatment and control are as even as possible within each cluster. Okay, so now let's go ahead and use that last one on there because I feel okay with the numbers I got. You'll notice I don't have any zeros on here. I don't have any, it looks like it's 50-50 overall. So let's go ahead and just, for treatment and control, let's go ahead and, see what happens if I generate a response variable. Okay, so what I'm going to do, I am going to create a fake response variable. I'm going to call it response. And I'm going to make it so that hair has a bigger effect than any other variable. And then I has a bigger effect than sex and treatment. Sex has a bigger effect than treatment. All right, so what I'm doing, I'm setting it up so that those nuisance variables that I know are influencing the results have a larger impact than what it is I'm actually trying to study. I'm trying to study the treatment, but these other variables are known to have an impact on what I'm interested in, and they're really just a nuisance. They're getting in the way. They're obscuring what's going on. Okay, so these blocking variables are obscuring the effect of the treatment. All right, so that's not ideal, but that's how real life works. That this could happen. On top of that, I'm going to make it so that the standard deviation of the noise is as large as the effect of treatment. Okay, so I've got 3 nuisance variables obscuring the effect that I want to see, and the noise has a standard deviation equal to the effect of the treatment. All right, so I have stacked the deck so that it's going to be hard for me to pick up on what's going on. If I did not do a good job in my experimental design, I don't have a prayer of figuring out what's going on. Okay, and also to take it even a step further, I'm not using pooled variance. I'm going to be doing my t-test in a manner so that I'm more prone to fail to reject the null hypothesis and conclude that there's no treatment. All right, so here is my code for computing the the response variable. All right, so I'm saying the 4 levels of hair have an effect of 8, 7, 6, and 5. Eye color, has I believe 2 values each. Is it hair, then treatment, and so on. And so I also put on standard normal as my noise aspect. I put on an intercept of 8. And now let's run a t-test on this. Okay, so notice that my p-value is 0.005. All right, so at a risk tolerance, an alpha value of 0.01, we would reject the null hypothesis in favor of the alternative. We would conclude that treatment and control have different values. All right, and also I did a 2-sample test, so that's doubling the p-value compared to a one-way test. All right, so I have stacked the deck as many ways as I can to make it so that my test would not detect the results, but yet it did because clustering came through on this example. All right, and so I've got a confidence interval on the difference. I've got the mean of X and the mean of Y, and you can see that there is a different, the effect size between them, the difference is just 1. All right, I really did not have a whole lot going for me in the setup. If I would have messed up the blocking, those nuisance variables would have obscured the result. And notice that the default variance in our norm is 1. So the standard deviation is 1, which means that I have as large of a standard deviation in my noise data as I have effect size I'm trying to detect, yet I was still successful. And I ran this multiple times, every single time, and it was always a reject the null hypothesis in favor of the alternative at 0.05 every single time I ran this. Okay, so now let's take a look at box plots just so that we can see like what's going on. So I can show you how much the nuisance variables were a nuisance off of this. All right, so here is I'm going to shrink this just so that we can see this. So here is the response by hair. And so when we see boxes in very different vertical positions, that's evidence that there is something going on. And so we can just see that like brown and blonde are very distinct. I set it up so that it's they have 8, 7, and 6 as their effects. With one of them, I guess it would be brown, would be the baseline level because of how I did the dummy variable aspect. I dropped the baseline level, which was the most frequent of them. All right, and so once again, we can see that there's definitely something going on between brown and blue. I know that there's something going on because I wrote the code. And then we go to sex. And you can see as I scroll down, remember I had the effect size get smaller and smaller as we go down, as we go from left to right on that data frame because of how I wrote it. You can see as I go towards the right of the data frame, we're seeing less of a distinct effect. Visually, like a visual hypothesis test would not detect the difference between sexes. Now here's my cluster. So remember that clusters have homogeneous groups, and each subgroup has an effect. I made sure that hair had a significant effect on the response. I made sure that sex had an effect on the response. I made sure that eye color had an effect. So it's natural for all of the different box plots to be at different levels because that's how I built it up. I'm trying to make the nuisance variables be nuisance. It's easy to detect the differences in the clusters because of how I built it. It's not so easy to detect the treatment, but yet we do. Now, visually, there's not much of a difference here, right? Visually, control and treatment, it's hard to detect that difference on there, but we were able to because I made sure that everything worked out. All right, so I hope you've enjoyed this video. Clustering is a good way for us to figure out our blocks when we have a lot of nuisance variables that we need to account for in blocking. All right, well, life is short. Do math.